I'm happy to be here. I hope you take something out of my talk. So the title is Photovoltaics Deployment and the Need for Recycling, with some observations about the special case for Argentina. So I'm Taretto. I work in Argentina as a scientist and a professor in photovoltaics. And this talk was prepared with the help of Enertrag, a student of mine. So to begin with, this is the outline of my talk. First, I will talk about the deployment of solar energy, the state of the art in the world, and particularly in Argentina, where I will show you also the, very briefly, the regulatory framework that led Argentina to slowly grow in the photovoltaics technology, and then try to identify a couple of barriers I elaborated with a couple of colleagues quite recently. Barriers to further development, I mean. In the second part of my talk, I will talk about recycling, the recycling of traditional modules. More than 95% of photovoltaic modules are called traditional because it's the silicon technology, and this is what I will be talking about. What is the state of the art worldwide about recycling? How can we forecast the demand for recycling modules? And how can we apply this forecasting model to Argentina? And finally, I will give a technology overview about recycling possibilities. So, yeah, let's start. The solar deployment around the world, I'm sure you have seen a lot of enough graphics about the growth of renewable energy along the years. This is a different way to look at it, and it's a comparison between the year 2019 and 24 of the investments done on renewable energy. Renewable power is here marked in blue. So, and these are the different countries or regions, and you see that between 5 years ago and now, all these countries or regions, more or less all of them, increased notably the investment in renewable energy, of course, including solar. But is this enough? Well, this is a plot of the percentage of electricity participation of renewable energy, solar and wind specifically. And this is the path we are being following up to now. We are entering this slashed line here. And this is the path we should follow if we would accomplish the partial targets of the Paris Agreement about mitigating global warming. So guess what? We're falling short. We're falling short in order to comply with these requirements. So this is one point. So different countries are making different efforts to do this. Most of the countries committed to the Paris Agreement. What happened to Argentina, who also committed the Paris Agreement, right? Well, Argentina is a very sunny country. I guess you know that. This is a map of solar energy. This is the yearly mean value of solar energy on a square meter. And you can see we have regions with very high solar energy. In particular, this point here is this point in the world with the highest solar energy along a year. You may think about Sahara, but Sahara is not as high as this, where you have 4,000 meters above sea level. For comparison, the solar energy levels are, for example, in southern Germany, which is sunnier than the north, are around 3 and 4. So Germany is below the half part of the scale. But we have a lot of solar energy. Of course, the first installations of solar plants are done in these areas where you have the highest radiation levels. But this is very recent. The installations began in 2010. Here we have, on the right, we have the installed photovoltaic capacity in megawatt peak. So we just surpassed the 1 gigawatt peak. The generation goes hand in hand with what you install, of course. But you see that this is a very particular development curve, right? So we have a lot of solar energy available over very vast areas, but we have issues that made us slow down the installation. Let me get a brief introduction about the regulatory framework which constrains this evolution, right? And there are public policies in Argentina. There are regulation laws and there are promotion programs which have different targets. For example, this is a program to facilitate renewable energy to rural areas. This is a program to facilitate the proliferation of renewables for large users like industries, or this other program promoted the installation of larger solar plants, for example, via tax reductions or custom duties reductions, for example. And in this recent publication, we tried to figure out what was going on with Argentina and compared it with Australia and Chile. They have similarities. They have similar solar resources, these three countries. Australia has a higher per capita income than Chile and Argentina. And nevertheless, Chile reached the gigawatt peak capacity a couple of years after Australia, like 5 years. And we took another 5 years to reach the levels of Chile. So we had different slowdowns. The part where we have seen an increase in solar energy installation had to do with these programs I mentioned here and here, but different barriers slow down the installation in different opportunities. For example, we identified here the lack of the allocation of these financial resources. Also political disagreements between different political contenders, high consumer side subsidies, which demote the use of other energy sources, also in particular renewable. And this can be seen, for example, if you take the average retail electricity prices per kilowatt hour in terms of dollars here, Argentina is about 1/3. If you look at the numbers, 1/3 compared to Chile and Australia. Also, as we stated in this paper, I just quote this, there exists a knowledge gap between the many well-trained scientists and technologists and the player in the upper strata of the political decision-making system, who often lack the necessary policy development tools. And finally, we also have a technical barrier, which is we require investments in the high voltage grid in order to drive all this renewable energy located at different parts of the country towards the bigger centers of consumption. But anyway, with all these installations, we see that the numbers are growing not only here, but also in several different countries. And this raises the question about recycling, of course. So let me give you first a state of the art around the world, what is being doing with recycling. First, let us just estimate how much there is to recycle out there. This is a graph which you must have seen in different ways. This is the time in years and the cumulative installation of here photovoltaics, but there are similar graphs, for example, for wind energy. So the voltaics is, this is 2023. So it's expected to by the end of this year to reach the 2 terawatt mark. So how much is that in terms of recycling? If we have 2 terawatt of modules, which are just now starting to fail massively, because the timescale here, these are up to 2024, we have 20 years since the, let's say, photovoltaics installation has become massive. So just now we have a very large volume of modules to be recycled. So we can say for 2 terawatts, if each module is 500 watts, we have 4 billion modules to be recycled. So if the lifetime is 30 years, this means a mean amount per year to recycle of 3.3 million tons per year of panels to be recycled, right? Is this a lot? Is this not a lot? We can compare it, for example, with the plastic waste. Plastic waste worldwide is 220 million tons per year. Okay, so this is a figure to bear in mind. Is there any significant recycling around the world? We need 3.3 million tons a year. Well, this is the evolution of just the amount of PV waste, photovoltaics waste collected in tons. So we have several companies now. In 2024, there are 177 recyclers or pilot lines. And in total, in 2021, this was 30 tons of collected material. Perhaps it's 100,000 tons, much less than what we need. We need this 3.3 million tons. In this report by the International Energy Agency, they say that although they have this, there is limited information about what is the real capacity of all these plants to process PV waste. Also, what is the output? So it's not clear which of these projects are profitable, for example. So it's unclear how much and how efficiently the recycling is going on. It's very recent. Nevertheless, they say that if you see the trends in global publications, patents about recycling and research activities, it's just that this is still will be growing for several years. The profitability of these projects is not known. It's yet to be determined, and it will depend on several factors, countries, techniques, not clear as of now, according to this report. Which, by the way, if you're interested in this topic, I recommend you to look for it. It's free to download. Let us try a very brief, how do you model the forecast for the recycling demand? In the case in general, but also in Argentina. This student of mine made her master thesis about recycling modules in Argentina, which is Argentina is not recycling modules as of now. So how do you do this? Well, there is this Weibull function who gives you the failure probability. This function is well known in many technology aspects. For example, parts, industry parts or devices, they tend to fail according to this distribution. For example, if 30 years is the lifetime, well, this is the probability function for 30 years projected lifetime of a module. And the spread of this bell-shaped curve has a factor of a geometric factor, which was determined empirically by different studies. So this is a number which gives you how much the function is spread. So you can see that maybe although the lifetime is 30 years, maybe at the year 10, you have a couple of failures, right? And if you fold this probability with the amount of installation for a given country, for example, Argentina, you will have a curve that shows you how much you have to recycle every year. So this is what Ines calculated. And for example, for the forecasts of installations in Argentina, you will get a forecast for recycling with a peak in the year about in the year 70 of the equivalent of 500 megawatts in modules. Yeah, this implies, for example, 25,000 tons of material to be recycled. Also, you can repair modules. This is not taken into account here. A very brief overview before reaching the end of my talk is, well, what is there to recycle in a solar panel? It's a really simple device, actually. You have solar cells. The solar cells are made of silicon. There are some soldering strips, metals like copper, tin, lead for the soldering. The cells are glued together with some polymers to the glass, which is in the front. And we have an aluminum frame, and we have a junction box, which is plastic in the back. So the process steps for the recycling are first to remove the frame and the junction box, and then you have this, what we call the laminate, which is all these sheets glued together with the cells. And there is a number of ways to separate them. One is mechanical, then you have thermal, you put everything in an oven, or chemical, of course. And then you can start thinking about recovering the material. This is the weight distribution. This plot here is the weight distribution in percentage of the total module weight. So 70% is glass, then you have 18 is aluminum. And for example, then you can look at silicon, 3.6%, but it's very, very sparsely. And then you have a small amount of silver and other metals. And we could say, well, it's negligible, right? But if you take the total amount of silver used every year for the production of solar panels, you will notice that 18 of the whole world silver production goes into the photovoltaic industry. So that must be a lot of tons of silver there to recover. This is some examples of recycling facilities. This is in Germany, Lohse Chemie. They mechanically separate the glass using a high pressure water. So this is a mechanical process, and they separate the laminate from the glass, and they get perfect sheets of glass to be reused. With the remaining, that's the glass sheet, now without the rest of the cells and everything. And on the other hand, they have a mix of the silicon and the plastics, which they separate then and then get silicon. They separate this chemically. They put everything in a big recipient and separate chemically using different processes the different materials. Also, this is another company in France. I'll have to let me go back a little bit. They separate the frame, the junction boxes, which are plastics to be recovered, and then the glass and the silicon. They will show you now that they separate up. Well, it's not shown very clearly, but they crush the panels, and then they crush it again into a smaller scale until you can separate by different mechanical methods. You can separate the silicon from the plastics and the glass. So here they get almost pure glass and silicon on the other side. Finally, this is another approach applied in Taiwan, which is to put the modules in an oven, and then can separate the cells individually. very neat. They can apply different chemical processes and obtain the silicon wafers, which they can reuse and do new panels. And this is actually working, as they claim. This was then a very brief overview of the variety you have in recycling solar panels. Yeah, so these are my conclusions to this brief talk. So we noticed that photovoltaics has reached a large scale. It can play a substantial role in mitigating global warming and supporting sustainable human development. Now, the deployment of photovoltaics depends on the region or country. Despite international agreements like Paris, each country faces unique technical, economic, and political barriers. I showed you a couple of these for Argentina. Now, the extensive use of photovoltaics increases the urgency of developing efficient recycling pathways, because the majority of decommissioned modules go right now into landfills, okay? And finally, the good news is that module recycling is feasible through a variety of techniques which we already know. So there is some flexibility for different pathways according to different recycling goals. Yeah, so that's the end of my talk. I hope you enjoyed it. Danke für die Aufmerksamkeit. Thank you.
Thank you very much, Kurt. And now we welcome Alejandro to share his presentation and give us the next talk.
Okay, good morning, everyone. Good afternoon, depending on the part of the world you are. 1 second, please. Do you see my presentation mode?
We are not seeing your presentation yet.
Okay, wait a second, please.
Oh, now it's coming.
We are seeing your screen, not the presentation mode. You can change here in display settings. You can change the monitor that you are sharing.
Wait a second, please.
Yep.
Okay. Now you see normal. Now should be a presentation.
Exactly.
Now
You can start the present. Now it's perfect.
Now it's
okay. Okay. So first of all, thank you very much, Flavio, for the invitation. Glad to know you, your colleagues, and to be here. Agustina also, she took all the time for discussing the details and organizing and the power behind the scene. So thanks a lot for your coordination. So welcome to everyone here. The idea today is to go through the synthetic fuels production, talking about decarbonization of the CO2, or defossilization of the CO2, better said. And let me start from the beginning. I guess we have students from a broad variety of knowledge and experiences. So please let me go through a very basic definition. 20, 30, 40 years ago, we have been starting discussing about renewable energies because of making use of fossil fuels and extinguishing resources which were not renewable, oil, gas, wherever. Years after that, this paradigm has changed. We have now a new paradigm, meaning that we will not survive if we consume all reserves we already have. It's very different, the message from the very beginning. We are talking about sustainable human development, and we are not talking about the consumption of products which are being extinguished due to the human action. We are now saying that if we consume what we already know we have, the human life will change radically as we know it. Let me say why are we talking about this today? Let me ask you a few questions. First of all, are we living in a future which has been identified, dreamed by Jules Verne 200 years ago? The energy transition requires structural changes in the global economy. And finally, the global transformation of the energy, gas, and transport systems is not only the energy. When we talk about energy transition, we are talking about three streams of work: energy, gas, and transport. And we will go through this during this presentation. And some questions for the students. A question we did ourselves many times, 20, 30, 40 years ago. Why I am going to study this subject if I am not going to use it anymore? So people loving books said, I don't want math. People loving math said time ago, I don't need to read a story and make a summary for my teacher. Let me go through this at the end of this presentation and saying, guys, everything is linked to everything. And in this particular environment, university environment, it's very important to answer this question always in the same way. 30 years after we did this question, we are coming and saying, guys, I am working and need to study chemistry because now I am talking about electrons and now molecules are going to be mixed within the business cases. Let me start from the end, but a well-known author of many books and stories already predicted what we are living. And he said that I believe that one day water will be the fuel, that the hydrogen and oxygen that constitute it, used alone or together, will provide a source of energy and light. And this was said in a book in 1874. The book was The Mysterious Island and has been downloaded many times since we started now bringing back his ideas of Jules Verne's, saying that we will use water as a fuel. Please remember when he said this. When the trains in the industrial transformation in the world were running with coal, in never way could be said that the water was a fuel by persons that in that moment were living because of carbon. I will come back later on, but now we are living things which were said 200 years ago. The energy transition goes through energy, transport, and gas. I will leave this. I will not go through this because I am sure you have enough knowledge to go through, but it's a reminder. We are used to know that wind turbines, PV panels, like Mr. Taretto mentioned in his presentation. Thanks also, Kurt, for this. I was learning also now many things from you. Glad to know you are there. You have many things which were used for us, introduced by many teachers I had in Germany, for example, during, I don't know, I was living in Germany during more than 12 years. And there we were talking about energy, but they always said, guys, it's not energy, it's energy, transport, and gas. Well, wind turbines, PV panels, biomass, hydropower, this is energy. But guys, do not forget, transport and gas are part of the equation. Well, again, back to the wind turbines, Hanover Messe, Hamburg Messe, Husum, and so on in Europe. Energy. And always our teachers saying, guys, do not forget, transport, gas, and energy. It's not energy only. And now we are living this. And this is the aim of this presentation. And the question to all of you is, what is changing now in the world? The answer is very easy. Everything, guys. Now it's everything. Now it's not wind turbines, it's not PV panels, it's not biomass, it's not everything behind this. Thousands of PhDs, masters, students, industrial actors, everyone coming here. And now the title of my presentation, synthetic fuels, fuels without fossil CO2. And now we will see what is changing now. And now we are talking about P2X converting renewable energy into fuels, chemical or heating and cooling. Again, the answer is everything to the question, what is changing now? Agriculture, chemical industry, fuels for transport, aviation, ship, maritime industry, heating, cooling, everything now is being in a transition towards synthetic creation of the same molecule. Before I go further, the molecule is the same. Please do not think that we are talking about a different molecule. Now, we have been talking about electrons, cables, but now we are talking about those electrons powering units which are producing molecules. But the molecule is not changing. Chemics are not changing. Physics are not changing. We are using them now. And the other good news is that we are using proven technology. We are not asking ourselves, for example, if we can electrolyze water. It's proved, it's there. But now we are bringing this to a new level. We are bringing this to a next generation. What are we talking about? Please go in this very, very basic scheme from left to right from your screens. We are talking about large amounts of new renewable energy. Please take care of the word new. It's not already installed power. We are talking about thousands of gigas which are going to be installed and are already being installed to power this chain. Then we need to handle large amount of new renewable energy in the grids. We have a huge task of grid integration. And now new actors, new friends in our constellation, in this universe. Again, please, I will repeat it until the finalizing this presentation. Energy, transport, and gas, not only energy. And now we have actors which are loading the system. Electrolyzers, the biogenic carbon capture units, and the synthetic fuels synthesis system, which are for ammonia, for methanol, for whatever. But we have large units which are going to be new in the system. And finally, the challenging of logistics, bringing everything to the consumption places. But how is this distributed? In this way, guys. If you see it again, left to right, you generate energy, bring those large volumes of energy to the grids, which are powering the electrolyzers, which are powering methanol units. In this case, I am using the example of green methanol, where I am also powering the CCT capture, the capture of biogenic carbon, and then producing methanol, transporting it to the local harbor, and then bringing to the world. From where? From places where I have unique resources of wind and PV combined, from places where I have biogenic CO2, ethanol, or paper, cellulose, for example, and bringing them to the consumption. Places where in the world are looking forward for green fuels, synthetic fuels. Non-fossil CO2 is being consumed. And this is a great good news. I will come back to a bit of geopolitics here. But let me make it a bit more complex, trying to do it as we do it in the university very fast now. We go from a nature-dominated energy system. Wind and sun are dominated the systems. 200 years ago was said that water is going to power our system. Please remember that. In this process, the water electrolysis creates hydrogen from one side, oxygen from the other side, and then we use this hydrogen as a fuel. But now we have, at the end of the days, money ruling our system. Can I pay it? Can I afford it? Is reasonable? How can I do it? And then it comes a little bit interesting for us when we need to talk about economy. The levelized cost of energy for wind and PV, together with the levelized cost of hydrogen, together with the levelized cost of CCT, meaning the cost of tons for biogenic CO2, brings me to the value of the levelized cost of methanol. These projects now are very, very different from the projects we saw at the very beginning. I am coming from a world in Germany where when I use the mouse, do you see my mouse in the screen?
No.
No, sorry, I have the pointers here. Sorry, now yes, you see the pointer.
Now, yes.
Thanks. We are coming from a world where we saw the PV units, the PV parks, the presentation done by Kurt. We saw the wind farms being integrated, smaller and then larger, bigger, more efficient, larger wind turbines, better PV panels, more efficient per square meter, and so on and so on. But we are coming from this world here. Then we started very, very slowly in Germany talking about the electrolyzer. Not only Germany, Japan also, South Korea, the US, Canada, among others. Then the synthesis. The typical oil and gas industry we know, creating methanol, creating ammonia, time ago using fossil CO2. But now we need to be the CO2 biogenic, meaning non-fossil CO2, which looks like difficult to understand. And then we have a certain degree of discussions of issues we need to develop, maturing during a certain degree of years until we can install these projects. These projects are starting from a small-scale projects of 2 to 4 billion euros until 20, 40, 45 billion euros. Again, the scale is different. The engineering behind is different. And we come from a few hundred million euros for a large wind or PV park to billions in a pilot level. And then the discussion here comes about what are we transporting? Again, I will not jump in here because this is matter of typical lectures for a master or a PhD, but we are discussing a trade-off between transporting electrons, transporting molecules, transporting hydrogen, transporting methanol until the site of delivery, from the site to delivery, and so on, making the better price, making this affordable, trying to pay the levelized cost of methanol and compare apples with apples. At the end of the day, I am comparing a ton of methanol. The molecule is the same. The origin is different. The green CO2, the biogenic CO2 is the difference. The green energy, the green hydrogen is the difference. And the challenge for us is to make it affordable. And the scale is the discussion. When you have economy of scale, this is affordable. The prices are close to the industrial prices nowadays. And then the green industry is taking place nowadays. Example of what we are doing here when it comes to a project and sensibility analysis. Again, the final product of this is, and the discussion is, how much it costs. The cost of ton of methanol. Can I pay it? Well, you need to focus in some areas which are more or less relevant in terms of your price. Here you see who is really influencing the cost of methanol when you produce it in the chain I showed before. The renewable energies, the electrolyzer, the synthesis of the green fuel, in this case, methanol, and very important, the financial and taxes, the financial costs of the capital you need to use. Summary here, I am starting to finish the presentation, trying to keep in mind these 20 minutes of this presentation for today. We have a primary electricity world where we are coming from. What we saw today, what we will present any standard conference in renewable energies. large volumes of renewable energies powering our life, our daily life. Some countries more, some countries less. Everyone running already since more or less 20, 30, 40 years, depending on the region of the world, trying to trigger the industry to install those machines which are sustainable and renewable. But then comes the electrolyzing. And then the question is, which kind of energy shall I use? Shall I use cheap energy? Shall I use expensive energy and make it more where I can add value to direct hydrogen or to derivatives of hydrogen, ammonia, methanol, crude iron, many things like this will change now to a green steel industry coming from a green iron industry using green hydrogen, for example. It's not only ammonia, it's not only methanol, it's the whole world which is changing. Let's talk about geopolitics in the energy transition. Again, please don't take it as a full report. This is only a summary of the situation. We could talk hours about this. It's a very, very interesting thing. But you have three kind of countries. We have the countries which are self-consuming, you have regions or countries which are netto exporters. You have countries or regions which are importers. And initially, high level, you can see here that the US and China are typically nowadays mentioned as consumers, self-consumers, large markets, but producing what they need. That means when you talk about exporting P2X, typically you are not including them, not because they are not relevant, because they are producing their needs. Typical areas, South America, the southern part of Africa, are regions which are believed to be the producers of large amount of green fuels, synthetic fuels. Typically to whom? Europe, South Korea, partially Australia, which has two roles, exporting and also consuming certain kind of them. Would be hours of discussion if you put here on top of this a layer of politics, kind of governments, left, center, or right in the history. If you talk about the development of patents of technology for renewable energy, wind, PV, who are the countries doing that? If you put the wars, which are a very sad event we have in the world, and if you put these layers, would be much more clear who is triggering the consumption of these kind of technologies and who is making a delay of these kind of technologies, pushing the world to one direction or the other. Let me start finishing this in more university typical integration of knowledge. But the good news is that it's not only engineers, owners of this solution. We are typical engineers, proud of our career, of our title, and we see us as the key part of the world. Without us, no one could do nothing. But guys, welcome to the reality. We have energy economy, we have political and legal sciences, we have environmental sciences, we have also social psychology involved, we have education sciences. Without all of these actors, no way to create the knowledge we need. I will come back to this. The cities are the small unit of the energy transition. Again, remember, energy, gas, and transport, not only energy, not only wind turbines, not only PV panels. And we have from entrepreneurs, startups, until multinational companies, a broad spectrum of companies who can provide solutions and bricks in the wall of the P2X building. We have a big building to build. We did the first two big stages, but then we need the fourth, the fifth, until number 50 in the world. And now we are start running from having been working during 40 years. Let me finish to bring you to the context when it was said what I said at the beginning of this presentation. an inexhaustible source of energy and light with an intensity that the coal cannot. Please refer this. This guy was talking about intensity in the energy source. And he said that will be heated by water. But when was it that? During the second industrial revolution. Please keep this in mind. Trains, expansion, development of the steel and the coal industry, machining and assembling lines. Colonialism was there. Steam engine for trains, for factories, growing cities, bringing workers to those places. No way to see the water as a power source. Please bring your mind in that moment. And you are talking nowadays about the generation of the WhatsApp, of Tesla, of the iPhone, of ChatGPT, and wherever we are seeing. But please keep your mind, when this guy mentioned this, he was talking about heating with water, using the word intensity and lack of intensity from the coal. The question is how we react to new technologies. Are we really proactive? Are we really thinking how to do the things better? Sometimes yes, and sometimes no. Year 1900, demonstration against the car. 50 years after, demonstration against the TV. 88 years after, demonstration against the calculator. Only a few examples of people swimming against the current. Nowadays, demonstrations against artificial intelligence. And what else is coming? The question is, are we learning from our mistakes from the past? Are we learning from people with more knowledge than us? Are we improving really? Answer is up to you. Finalizing my presentation of today with my last two slides, I have a very brief message, but I hope important for you. We are in a generation, from my point of view, which is a transition generation. If I mention the amount of technologies with my 47 years old I have been using since a diskette in a PC, MP3, and the Spotify world, the energy, cars, internal combustion. Nowadays, I am using batteries. Using meaning industrial developed, not dreams of Jules Verne. We are really in the most challenging generation we can see. We have seen industrial transitions, coal, heating, but that's it. Not 5 ways of trains during those times. Nowadays, we have those 5 ways of trains. Very, very fast, guys. We were talking about our sons, our grandsons. No, we are seeing and using and creating those technologies in an industrial productive way, not prototype from a lab. And that's why I would like to finish with one very big statement, which is a challenge for everyone who is in the university. And the challenge lies in training the new generation for technologies whose existence and development we're not aware of today. We don't know what is coming, but I need to prepare your brains to create things which I do not know. Because I saw it, and it happens to me when I started with the 2-blade wind turbines in the University of Stralsund and very small H2 unit for electrolyzing. 5 years after, someone is talking about 10 gigs of electrolyzing. So I need to prepare people to handle technology which I do not know. And it's the difference from the very beginning, from a very easy book to a book which has not been written. This is the challenge. Before finishing, I would like to use the chat here. If you give me 1 second more. If you see this slide, I know everyone knows this slide. This is a NASA picture from a satellite with a picture of the world. the typical, many of us, we have had them in a screensaver, were nice to see and so on. And please, I ask the students connected here, all of you, of course, let me know. I use it when I have a lecture, and it's an exercise of mine. What do you see here? Which is the message here? Two words, three at the most, please. I see the chat here. Light, responsibility of the bright areas, centralization. Five seconds more, and I will tell you what kids of 10, 12 years old are always saying when I give a lecture in a school. Consumption, Europe densely populated, you are all right, but you see something more there. But we are adults. We are people with experience. Our brains are already formed. Waste energy. Yeah, you're going there. Night. You see something which is the inequality in the world. The places where you don't see light are places without human beings there? The answer is no. You see there only a few parts of the world with conditions, with energy, meaning access to information, health, industry, and so on and so on. And many of the kids many times said to me, and that's why I share this slide at the end, is that the resources are not well distributed. The opportunities, therefore, are also well not distributed because they are not getting access to the basics. A warm bed, a book, health system, and social security, access to the university. And if you tell me that no one is living in the dark areas, would be fine. Now we have a population problem, but we all know that you have millions of people living there. So that's my last slide. The challenge is that makes the world more equal, more distributed, more from bottom up, not top down. And this is the last slide of mine today. Thanks for your time. Again, thanks for your this invitation, and available, of course, for any question you may have.
Thank you very much, Alejandro. Then we move to the next and last presentation for today. And at the end, we expect to have a nice discussion. Nils, please, you are welcome to share your screen and start your presentation.
So do you see my correct screen?
Yes, perfect.
Perfect. All right. So yeah, also a warm welcome from my side, and thank you, Agustina and Flavio, for hosting this. I know those two guys for many, many years, and Flavio asked me to give you a small insight into the energy transition situation within the steel industry, and that's what I'm going to talk about today. So let me give you a brief heads up of who we are. So the SHS, the Stahl Holding Saar, where I work for, is a management holding above the two steel companies, Dillingen and Saar, located here in Saarland. We also have plants in further areas in Germany and also in France. Plus, we are a global player, so we have distribution structures all over the world, for example, in North America, South America, in Europe, in the greater area of Asia and the Middle East. So we have global market, global competition, and therefore, which will be interesting for the further talk, we also have a topic of global energy prices. So just a brief summary of how big we are. So we have around 6 billion in sales revenue. We have around 13,000 employees. So we are by far the biggest employer here in the region. And we produce around 4.1 million tons of crude steel. So what are our products? You have to understand our products in order to understand the energy transition we are facing. At the Dillingen side, we have one major power supply key industry. It used to be the biggest one. It's, for example, oil and gas, transportation, pipelines. But in the recent years, like the past 4 years, that shifted to the renewable energy production. So when you see an offshore wind farm, for example, everything which is below the sea level is from Dillingen, and especially the monopiles. The monopiles are the foundation of each windmill and is actually in the ground. So it's the foundation of every windmill. But we have other key industries, for example, the machinery, heavy machinery, mechanical engineering, bridges, all where we need heavy plates, heavy sheet metal is part of the Dillingen side. And then we have the Saar, totally different market. It's more like the long product market. It's everything which is thin and long, for example, the automotive industry, springs, for example, or the wire rod in tires, that comes from Saar. Around 60% of the market is the automotive industry, which is a problem at the moment. I mean, you only have to open the newspapers where you see that the German automotive industry is struggling at the moment. That's a problem for us as well. Then we have the mechanical engineering, rail infrastructure with our plants in France, and other construction sites. Now, you have to understand the process of how we produce our products at the moment. I don't know whether you've been able to visit a steel company in the past, but this is just a brief walkthrough of the steps we are facing here at Dillingen at Saar. So the first step in producing steel is the pig iron and the crude steel production. As of today, by far worldwide, we have the production with blast furnace. After the blast furnace process, I'm not going to go into into technical detail here, but after the blast furnace, we have the basic oxygen furnace, and after that we have our crude steel. Now, crude steel is the basic steel for the secondary metallurgy, which will come after the first step. We have the secondary metallurgy where we get rid of trace elements. We have the casting process where we solidify the liquid steel into as a Dillingen as slabs, so-called slabs, and then we have the rolling mill process where we produce out of slabs the metal sheets, and at the end of the day the quality control obviously as well. At Saar, it's basically similar. They become the pig iron from Dillingen. They also have the secondary metallurgy. The casting process is a little bit different, so we don't have metal sheets, but we have wire rods, we have rails, and we have steel bars. But there's one important thing about the production side of today. It is a very highly integrated and efficient steel mill. So everything which goes into the process, coal, coke, iron ore, will be transformed into, at the one hand, steel, but on the other hand, we have other products. We have off gases. And those off gases are very valid to us. So as an off gas, for example, in the cokery, we have cokery gas. From the blast furnace process, we have blast furnace gas. From the converter process, we have converter gas. And those gases, for example, the cokery gas, has over 50% of hydrogen. So there's lots of energy saved in those gases. And those gases are being reused to, on the one hand, fire the ovens, and on the other hand, to produce electricity. So at the Dillingen site, for example, we produce our own electricity and have only a very small portion of electricity from the grid we have to buy. And now, with this process, we still have a big problem. And the big problem is CO2. It's a very CO2 intensive industry, the steel industry. So the question is, well, the CO2 is obviously an economical and an ecological problem. Economically speaking, we have to buy certificates. For each ton of CO2 we pollute, we have to buy certificates. So it's expensive, and it will become more expensive in the future. And ecologically, well, it's not good for the climate, obviously. So we have to think about a way of how to produce steel in the future with less CO2 emissions. So we have to transform our production. And to transform our production, there is an energy transition. This is what I'm going to talk about in the next slides in order to reduce the CO2 emissions. And believe me, this project is disruptive, a mind-blowing disruptive way. Well, it's surgery on an open heart at the moment at our sites. So to give you some steel facts about Germany, we have a crude steel production of around 37 million tons per year. That was 2022. At the moment, it's decreasing, unfortunately. We have around 50 million tons of CO2 emissions in the steel industry, and our power consumption is around 25 terawatt hours. Now, what's the portion of CO2 emissions for the steel industry in Germany by sector? 8% of all CO2 emissions in Germany come from steel industry. So it is a heavy amount. And our portion of that is around 1%. Now you can ask yourself, which of those would be the best to transform in order to reduce CO2 emissions? And we all talk about hydrogen at the moment. And in terms of hydrogen, the potential of CO2 reduction, so per ton of hydrogen, is at the steel industry by far the largest. So in the steel industry, when you use 1 ton of hydrogen, you can reduce 26 tons of CO2 emissions. And that's the reason why it's worth to put money in the transformation of the steel industry, which also the subsidiaries of the federal government did in the past. I mean, I guess you all heard about it. The steel industry are being funded at the moment here in Germany by billions, but I think that's a good invest because the potential and the leverage is here the highest. So what are we changing at the moment? What is our transformation? Our transformation is the project name is Powerful Steel, and what we do is we transform our whole way of making steel beside the old route. And the major parts of the new route is building a DRI tower, that's a direct reduced iron tower, that's maybe the equivalent of a blast furnace, and EAF, it's an electric arc furnace. At the Dillingen site, we will get such a DIR tower, and we will get 1 electric arc furnace, parallel working to the conventional route. At Saar, it's about 20 minutes apart. We will not have a DRI plant because the cold DRI, the cold direct reduced iron, will be a transport from Dillingen to Völklingen to this site. and they get an additional electric arc furnace as well. And to give you some numbers about this, about the size of this transformation, we will transform 70% of our production capacity at once. We will use up to 100,000 tons of hydrogen at the final stage. And with this, we produce around 3.5 million tons of green steel. So this is around the 70% of our 4.5 million tons of steel we produce today. And all this will cost us around 4.6 billion euros. Obviously, we cannot do all the 4.6 billion euros by ourselves. So 2.6 billions is a subsidiary of the federal and the state funding. Without that, we couldn't have been doing this. So today, we have 2 blast furnaces and we have 5 so-called converters. And tomorrow, we're going to have 1 blast furnace. We're going to have 2 converters. This is a conventional old route. In addition, we will have the direct reduced iron plant and we will have 2 electric arc furnaces. And this is very important. I mean, all the people who live here in Saarland know that for the future of Germany and Saarland, because if you imagine we have 13,000 employees, direct employees, and many more indirect employees. So it's crucial that this project will fly. So now what does that mean in terms of CO2 emissions? Here in the first row, you see the blast furnace route. We have iron ore, coke, coal, natural gas. And at the end of the day, we have around 2 tons of CO2 per ton of steel. 2 tons CO2 per ton of steel. In the first step of our transformation, we will use the DRI-EAF route. In the beginning with natural gas, so 100% natural gas, no green hydrogen because it's not available. And even by using 100% natural gas, we will halve the amount of CO2 emissions. So it's only 1,000 kilo or 1 ton CO2 per ton of steel. So that's already a big step. And in the next step, we will use green hydrogen as a reduction agent to subsidize the natural gas. And by this step, we will again reduce the CO2 emissions by a lot. There will always be a significant amount of CO2 emissions left because we need carbon in the steel. So we have to add carbon, but it's way less than from the normal conventional route as of today. So what is the role of energy in this transition? Well, as I mentioned, the central energy source at the moment is coal. By far is coal. The energy procurement of coal, well, we have a global market with low cost desertification. So it's not that important where you are in the world to produce the steel. It's basically a same level playing field. In the future, it's not going to be coal. It's going to be green electricity and green hydrogen. And the energy procurement of green electricity and green hydrogen is not a global market. We don't get green hydrogen from Australia, sorry. It's not going to be, maybe it's going to be ammonia at the most, but it's not going to be hydrogen. So it's the significant global price differences for the commodities, electricity and hydrogen is crucial. And in other terms, the location factor is crucial. And now we have a small problem in Germany because in Germany, we don't have that much green electricity and we don't have that much green hydrogen. And this is at the moment a problem not yet thought through to the end. Of course, there are, we build up a hydrogen network in the future. We will have hydrogen imports, ammonia imports, but it is very local and European market price-wise instead of a global market. And this can be a problem in the future. So to show you about how much of energy we have in coal at the moment, you see this chart here. So we have around 21 terawatt hours of coal in our system, in our energy system here in Saarland. We have around 1 terawatt hours of natural gas and 1 terawatt hour of electricity. So in terms of energy, we have 23 terawatt hours in our system. Now, when we transform, coal goes down. There's only a little bit left of coal. Natural gas will be increased by a lot, by electricity will be increased by a lot, and of course, hydrogen and electrolysis will be increased from nothing to a very lot. So as you can see here, when you compare those two charts, you will end up that this route is more inefficient or less efficient. We have more energy in our system than before. And this is a comparative scenario. So if we want to compare the current status with the future, this is the truth. Now, we don't produce 4 million tons of green steel. We still have the old route, and we don't use a direct reduced iron to scrap ratio of 4:1. So at the end of the day, it will be similar to today, because we import scrap. We use scrap, and scrap is something which we did not need in that amount in the old route. So what I want to say is that the new route is less efficient, and this is something many people forget. We have a highly integrated steel mill at the moment where we use everything. Every exhaust gas is being used, every heat is being used, and we will be more inefficient in the future. That's something that's maybe a takeaway on for this slide. To give you another example of the energy demand, this is a standardized chart of a production of 1 million tons of green steel. As a reminder, we produce 3.5 in the future, but this is for 1 million ton of green steel. For 1 million ton of green steel, we need 15,000 tons of green hydrogen. This is around 30%. So 70% is still natural gas. And for this water electricity, we need 1 terawatt hour of green electricity. To give you an example, the power consumption of our state here, Saarland, is approximately 7 terawatt hours. So, and we don't produce 1 million ton, we put on 3.6 million tons. So you can imagine the significance in our area of our future electricity demand is huge. And what about the costs? So the role of the energy in terms of costs. We have our new production route. We need green electricity, we need green hydrogen, and we need natural gas. Let's make a small calculation. If we use at the very beginning 100% of natural gas, and we look at the energy prices in the exchange markets, we see a price of around 35 euros per megawatt hour. Plus, with natural gas, we have CO2 pollution, so we have to buy EU ETS certificates. Let's assume we have a price for those certificates at around 100 euros per ton of CO2. This is way more than we see at the moment. 100 euros per ton CO2 is around 20 euros per megawatt hour equivalent. So we end up at an energy price for natural gas of 55 euros per megawatt hour. Now, when we want to use hydrogen instead of natural gas, how cheap or how expensive is hydrogen to be in comparison to natural gas? And if you make those calculations, you come up with a number of around 2.2 euros per kilo. Euros per kilo is the normal is a normal way of the hydrogen pricing. And here comes a problem, because at the moment we have a current outlook where we see prices between 8 and 15 euros a kilogram. And this, obviously, you can see this doesn't match, right? We cannot we cannot produce for 8 to 15 euros per kilo of hydrogen. This doesn't sum up with the use of natural gas. So we have to cut the costs for green hydrogen by a lot, and that's a major task in the future. Remember, SHS, we at the end of the day we need up to 120,000 tons of green hydrogen, and if you do the math, 120,000 times 2.2 euros mal 1,000, then you come up for the hydrogen costs we have, for the OPEX hydrogen costs we have, or if you multiply the number with 8 or 15 euros. So that's a significant difference. Another another topic, obviously, at the moment, I mean, maybe you've heard about it and you've read about it, are the grid fees for electricity. Let's assume 2020. This is so on the y-axis you see the factor of the price increase, and then the x-axis you see the year. Let's assume 2023 is a reference and is set with a factor to 1. We already saw a double in grid fees from 2023 to 2024. We will see a slightly increase in 2025, and the prediction, because of the energy transition globally or Germany speaking, will be up to 4 times of what we saw 2023. And already today, the grid fees reach a region of the same of the energy prices. So, for example, if we have energy prices of 90 euros a megawatt hour for electricity, we have the same amount of grid fees on top. And that's just going in a direction where we have problems to face those additional costs, yeah? Because our customers are not willing to pay that much more for a ton of steel, but our OPEX costs are exploding. So grid fees is a hot topic at the moment, and the government is thinking of having a new system of the grid fees. So this is something which we have to work on as well. So we have many tension between many areas at the moment. We have the politics. We have unstable political situations here in Germany at the moment. We have way too much ideological thinking for the market. For example, the start in hydrogen. If I tell you under what conditions hydrogen is green and under which conditions you're allowed to use this green hydrogen, you only have question marks in your head. It's mind-blowing. Of course, we need an import protection against China, because China is producing steel with subsidiaries also from the state, and way too much steel. And well, the steel gets exported to regions like Europe, and yeah, the prices are going down, and this is not good for us. We have green steel markets that needs to be established. We need a green steel premium. So who is willing to pay more for CO2-free steel, for green steel? The availability of green energy is mandatory to produce green steel, obviously. Plus, we need energy prices where we can produce in a way that we can have competition in the world market. And there's way more points, so there's lots of work to do at the moment. But I don't want to complain too much. At the end, I have a small project which is quite nice. So in terms of green energy, we also do participation in wind and solar farms. In wind farms, we have so-called PPA, purchase power agreement contracts with Iberdrola and EnBW. And in solar parks, we are currently in considerations on negotiations about regional PV projects. And with one of those PPA contracts with EnBW, we did a project. So we have a PPA contract with SHS between EnBW and us. SHS delivers the monopiles for the wind farm being built at the moment in the North Sea. SHS receives the electricity from the offshore windmill, and at the end of the life of the monopiles, those monopiles go back to the HSS, and the scrap is being remelted. Yeah? So it's a circular economy project we did with them, and it shows that it works. Yeah? I think you even read it in the newspapers, but this is a success story I want to share you at the end of this presentation. And as you see, there's lots of problems we have to solve in the future, but there's also lots of opportunities. I mean, at the end of the day, when we produce green steel and we are one of the first movers, I think there is a good opportunity to earn money with that. But the future will have to tell. So this is my small little story about the energy transition in the steel industry. Needs to be continued. We all have to work on that. And thank you for your attention.
Thank you very much, Nils, for this so nice history that you told.